Picture this, a single speck of light in the vast darkness of space, swirling with billions of stars, planets, and mysteries waiting to be unraveled. That speck is a galaxy, one of the countless cosmic wonders that make up our universe. But how did these colossal structures come to be? What forces shaped them into the breathtaking spirals, glowing ellipticals, and chaotic irregular shapes we see today? The story of galaxy formation and evolution is one of the most fascinating chapters in the history of the cosmos, filled with cosmic collisions, invisible dark matter, and supermassive black holes that defy imagination. In this video, we're diving deep into the heart of the universe to uncover 30 mind-blowing facts about how galaxies are born, grow, and transform over billions of years. From the tiniest proto-galaxies to the largest superclusters, get ready to explore the secrets of the universe that will leave you in awe. Stick around, because by the end of this journey, you'll see the night sky in a whole new light. Let's begin. Now, let's rewind the cosmic clock to the very beginning. The story of galaxies starts with the Big Bang, the explosive event that birthed our universe around 13.8 billion years ago. In those first moments, the universe was unimaginably hot and dense, a seething soup of energy and particles. But as it expanded and cooled, something extraordinary happened. Tiny ripples in the fabric of space and time began to emerge, fluctuations in density that would become the seeds of galaxies. These ripples were like cosmic fingerprints left behind by the chaotic energy of the early universe. Over time, gravity took hold, pulling matter together around these denser regions. Gas and dust began to clump, and the first stars ignited, lighting up the darkness. These early stars grouped together, forming the building blocks of the first galaxies. It's incredible to think that the vast, intricate galaxies we see today, each with billions of stars, trace their origins back to these tiny fluctuations in the primordial universe. The Big Bang didn't just create space and time. It set the stage for the cosmic dance of galaxies that continues to unfold even now. Now, let's shift our focus to one of the universe's greatest mysteries, dark matter. While we can't see it directly, dark matter plays a crucial role in shaping galaxies. Imagine it as the invisible scaffolding of the cosmos, holding everything together. After the Big Bang, ordinary matter, the stuff that makes up stars, planets, and us, was spread out thinly across the universe, but dark matter, with its immense gravitational pull, began to gather this ordinary matter into dense clumps. These clumps became the seeds for galaxies. Picture dark matter as a cosmic magnet, creating vast, invisible halos around galaxies. These halos act like gravitational traps, pulling in gas and dust, which eventually form stars and planets. Without dark matter, galaxies as we know them simply wouldn't exist. It's fascinating to think that most of the universe's mass is made up of this mysterious substance, yet we've only detected it through its gravitational effects. Dark matter doesn't just shape galaxies, it's the hidden force that keeps them spinning, stable, and alive. And while we're still unraveling its secrets, one thing is clear: dark matter is the invisible hand that guides the evolution of the cosmos. Now, let's take a step back in time to the very first galaxies that ever existed. These early galaxies, known as proto-galaxies, were incredibly small compared to the massive structures we see today. Picture them as the cosmic toddlers of the universe, tiny, fragile, and full of potential. They began to form just a few 100 million years after the Big Bang, when the universe was still in its infancy. At this point, the cosmos was a chaotic place, filled with swirling clouds of gas and dark matter. These clouds slowly collapsed under their own gravity, giving birth to the first stars and eventually the first galaxies. But here's the fascinating part. These proto-galaxies were nothing like the grand spirals or ellipticals we're familiar with. They were much smaller, often no bigger than a few thousand light years across. Over time, these tiny galaxies began to merge, pulled together by gravity. Imagine them as cosmic building blocks, colliding and combining to create larger and more complex structures. This process of merging and growing continued for billions of years, shaping the universe into the vast web of galaxies we see today. It's incredible to think that the majestic galaxies we observe now, like our own Milky Way, started as these humble, miniature versions. Their journey from tiny proto-galaxies to the giants of the cosmos is a testament to the power of time, gravity, and the ever-evolving nature of the universe. And as we continue to study these early galaxies, we uncover more clues about how the universe grew from its chaotic beginnings into the organized, awe-inspiring structure we know today. Now let's dive into one of the most dramatic processes in the cosmos: galactic cannibalism. Yes, you heard that right. Galaxies, much like cosmic predators, grow by devouring smaller ones. This process, known as galactic cannibalism, is a key driver of how galaxies evolve over billions of years. Picture this: a massive galaxy like our Milky Way exerts a powerful gravitational pull on its smaller neighbors. Over time, these smaller galaxies are drawn in, torn apart, and absorbed into the larger one, fueling its growth and reshaping its structure. Take the Milky Way, for example. Right now, it's in the process of consuming the Sagittarius dwarf galaxy, a much smaller neighbor that's been orbiting our galaxy for billions of years. As the Sagittarius dwarf gets closer, the Milky Way's gravity stretches and distorts it, pulling stars and gas away and adding them to its own collection. This isn't a quick process, it's a slow, cosmic feast that takes place over eons. But the result is clear: the Milky Way grows larger and more massive, while the smaller galaxy is gradually erased from existence. Galactic cannibalism isn't just limited to our galaxy, though. Across the universe, larger galaxies are constantly merging with and absorbing smaller ones. These interactions can trigger bursts of star formation, as the gas and dust from the consumed galaxy are compressed and ignited. They can also create stunning tidal tails and streams of stars, visible remnants of the smaller galaxy's final moments. What's truly fascinating is that this process isn't destructive in the way we might think. Instead, it's a vital part of how galaxies mature and evolve. Without galactic cannibalism, the universe would look very different: smaller, less structured, and far less dynamic. So, the next time you look up at the night sky, remember, the Milky Way and other galaxies are not just static islands of stars. They're living, growing entities shaped by the cosmic dance of gravity and time. And as we continue to study these interactions, we uncover more about the incredible story of how galaxies and the universe itself came to be. Now, shifting our gaze to one of the most breathtaking sights in the cosmos, let's explore the mesmerizing beauty of spiral galaxies and their iconic arms. These galaxies, with their swirling, pinwheel-like shapes, are some of the most common and recognizable structures in the universe. But what exactly gives them their distinctive appearance? The answer lies in something called density waves. Imagine a spiral galaxy as a cosmic carousel, with stars, gas, and dust all moving in a synchronized dance. Density waves are like ripples moving through this material, compressing it as they go. These waves don't move with the stars and gas. Instead, they travel through the galaxy at their own pace, creating regions where material is squeezed together. This compression triggers the formation of new stars, lighting up the spiral arms and giving them their bright, glowing appearance. But why are spiral galaxies so common? It all comes down to the way galaxies rotate. As a galaxy spins, its material naturally settles into a flat, disc-like shape. The rotation also causes the material to clump together in waves, forming the spiral arms we see. Over time, these arms can change shape, winding tighter or looser depending on the galaxy's rotation and the gravitational forces at play. One of the most famous examples of a spiral galaxy is our own Milky Way. From our vantage point inside it, we can't see its full spiral structure, but astronomers have mapped its arms using observations of stars, gas, and dust. These arms are home to some of the most active star-forming regions in the galaxy, where young, hot stars light up the surrounding gas in brilliant shades of blue and pink. Spiral galaxies aren't just beautiful, they're also incredibly dynamic. Their arms are constantly evolving, shaped by the interplay of gravity, rotation, and star formation. And while they may look delicate, these galaxies are anything but fragile. They're enduring structures that have persisted for billions of years, a testament to the intricate balance of forces that shape the universe. So, the next time you see an image of a spiral galaxy, take a moment to appreciate the cosmic processes at work. Those stunning arms aren't just random patterns. They're the result of density waves, gravity, and the relentless motion of the universe itself. And as we continue to study these galaxies, we uncover more about the forces that shape not just their beauty, but the very fabric of the cosmos. Now, let's turn our attention to the giants of the galactic world, elliptical galaxies. Unlike the graceful spirals we just explored, elliptical galaxies are massive, smooth, and often featureless, resembling glowing orbs of stars scattered across the cosmos. These galaxies are the result of some of the most dramatic events in the universe, galactic collisions and mergers. Picture this: two spiral galaxies, each with their own swirling arms and bustling star-forming regions, slowly drifting toward each other over millions of years. When they finally collide, their stars, gas, and dust are thrown into chaos. But instead of creating a tangled mess, the immense gravitational forces at play reshape the galaxies into a single, smooth structure. Over time, the chaotic motions settle, and the new galaxy takes on an elliptical shape, devoid of the spiral arms we see in younger galaxies. Elliptical galaxies are often found in the hearts of galaxy clusters, where gravitational interactions are frequent and intense. Their smooth, rounded appearance comes from the random orbits of their stars, which move in all directions rather than in a flat, rotating disk like those in spiral galaxies. This lack of structure gives them a more uniform glow, making them look like cosmic eggs or footballs, depending on their shape. But don't let their calm appearance fool you. Elliptical galaxies are anything but quiet. Many of them are home to supermassive black holes at their centers, which can influence the galaxy's evolution and even regulate star formation. In fact, elliptical galaxies often have very little gas and dust left, meaning they don't form many new stars. Instead, they're filled with older, redder stars, giving them a warm, golden hue. One of the most fascinating aspects of elliptical galaxies is their sheer size. Some of the largest galaxies in the universe are ellipticals, containing trillions of stars and spanning hundreds of thousands of light years. For example, the galaxy M87, located in the Virgo cluster, is a colossal elliptical galaxy with a jet of particles shooting out from its central black hole, a reminder of the incredible forces at work in these cosmic giants. So, while they may lack the intricate beauty of spiral galaxies, elliptical galaxies are a testament to the universe's ability to transform chaos into order. They remind us that even in the vastness of space, nothing stays the same forever. And as we study these galactic giants, we gain a deeper understanding of how the universe evolves, one collision at a time. Now, let's shift our gaze to the cosmic oddballs of the universe, irregular galaxies. Unlike the orderly spirals or the smooth ellipticals, irregular galaxies are the rebels of the galactic world, defying any standard shape or structure. These galaxies are a chaotic mix of stars, gas, and dust, often appearing as though they've been tossed together by some cosmic whirlwind. But don't mistake their disorder for insignificance. Irregular galaxies are fascinating laboratories for understanding the forces that shape the universe. So, what makes these galaxies so irregular? The answer lies in their turbulent pasts. Many irregular galaxies are the result of gravitational interactions with other galaxies. Imagine two galaxies passing close to each other, their immense gravitational pulls tugging and distorting their shapes. These interactions can stretch and twist the galaxies, pulling them out of their original forms and leaving behind a jumbled mess of stars and gas. In some cases, the gravitational forces are so strong that they trigger bursts of star formation, lighting up the galaxy with bright, young stars. But irregular galaxies aren't just the products of galactic collisions. Some are born irregular, formed from clouds of gas and dust that never quite settled into a stable structure. These galaxies often lack the organized rotation seen in spirals or the smooth distribution of stars found in ellipticals. Instead, their stars move in seemingly random directions, creating a patchy, uneven appearance. This lack of symmetry gives irregular galaxies their unique charm, making them stand out in a universe filled with more orderly structures. One of the most famous examples of an irregular galaxy is the Large Magellanic Cloud, a satellite galaxy of the Milky Way. Despite its close proximity, the Large Magellanic Cloud has resisted the gravitational pull of our galaxy, maintaining its irregular shape. It's a bustling hub of star formation, with bright nebulae and young star clusters scattered across its chaotic landscape. This galaxy serves as a reminder that not all cosmic structures follow the same rules. Sometimes the most interesting things come from disorder. Irregular galaxies also play a crucial role in the cosmic ecosystem. Their chaotic nature makes them rich in gas and dust, providing the raw materials needed for star formation. In fact, many irregular galaxies are hotspots for creating new stars, making them vital to our understanding of how galaxies evolve over time. They remind us that the universe is not just a place of order and symmetry, but also one of unpredictability and creativity. As we explore these cosmic oddballs, we're reminded that the universe is full of surprises. Irregular galaxies challenge our expectations and push us to rethink what we know about galactic formation and evolution. They show us that even in the vastness of space, there's room for individuality and chaos. And as we continue to study these unique galaxies, we uncover new insights into the dynamic and ever-changing nature of the cosmos. Now, let's turn our attention to the mysterious giants lurking at the heart of most galaxies, supermassive black holes. These cosmic behemoths, millions or even billions of times more massive than our Sun, are not just fascinating in their own right. They play a pivotal role in shaping the galaxies they call home. But how do these colossal objects form, and what exactly do they do to influence the evolution of galaxies? Let's dive in. Supermassive black holes are thought to form in the early stages of a galaxy's life. One leading theory suggests that they grow from smaller black holes, which merge and accumulate mass over time. Another possibility is that they form directly from the collapse of massive gas clouds in the early universe. Regardless of their origins, these black holes quickly become central players in their galaxies, exerting a gravitational influence that extends far beyond their event horizons. But their role goes far beyond just gravity. Supermassive black holes are incredibly active, especially during their younger years. As they consume gas, dust, and even stars, they release enormous amounts of energy in the form of radiation and powerful jets of particles. This energy can heat up the surrounding gas, preventing it from cooling and collapsing to form new stars. In this way, supermassive black holes can act as cosmic regulators, controlling the rate of star formation in their host galaxies. Interestingly, this relationship between supermassive black holes and star formation isn't one-sided. The growth of a supermassive black hole is closely tied to the growth of its galaxy. As galaxies merge and evolve, they funnel gas and dust toward their centers, feeding the black hole and triggering bursts of activity. This feedback loop creates a delicate balance. Too much activity from the black hole can stifle star formation, while too little can allow the galaxy to grow unchecked. One of the most dramatic examples of this interplay can be seen in quasars. the incredibly bright cores of distant galaxies powered by supermassive black holes. Quasars shine with the light of trillions of stars, outshining their entire host galaxies. Yet, despite their brilliance, they also play a role in shaping their galaxies' futures. The intense radiation and winds from quasars can blow gas out of the galaxy, halting star formation and influencing the galaxy's structure. But supermassive black holes aren't just destructive forces. In some cases, their jets and outflows can compress gas clouds, triggering new waves of star formation. This dual nature, both nurturing and disruptive, makes them key players in the life cycle of galaxies. They remind us that even the most extreme objects in the universe are part of a delicate cosmic dance, shaping and being shaped by their surroundings. As we continue to study these enigmatic giants, we uncover more about their profound impact on galaxy evolution. From regulating star formation to influencing galactic structure, supermassive black holes are central to the story of how galaxies grow and change over billions of years. They are a testament to the interconnectedness of the universe, where even the darkest corners hold the keys to understanding the brightest phenomena. Now, let's shift our gaze to one of the most spectacular events in the cosmos: galactic collisions. Picture this: two massive galaxies, each containing billions of stars, slowly drawn together by gravity, destined to merge in a cosmic dance that reshapes their very existence. These collisions are not just chaotic crashes, they are transformative events that play a crucial role in the evolution of galaxies. When galaxies collide, the process is far from instantaneous. It can take hundreds of millions of years for two galaxies to fully merge. During this time, their gravitational forces interact in complex ways, pulling and twisting their structures. Stars within these galaxies rarely collide due to the vast distances between them, but the gas and dust clouds within each galaxy are another story. These clouds slam into each other, compressing and heating up, which triggers intense bursts of star formation. This is why colliding galaxies often appear as bright, star-forming powerhouses, glowing with the light of countless newborn stars. One of the most famous examples of a galactic collision is the future encounter between our Milky Way and the Andromeda galaxy. Currently, Andromeda is hurtling toward us at a speed of about 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will begin to merge. The result, a completely new galaxy, often referred to as Milkomeda or Milkdromeda. This merger will dramatically reshape both galaxies, scattering stars into new orbits and igniting a frenzy of star formation. While the process will take billions of years to complete, the end result will be a single, larger galaxy with a unique structure and history. But galactic collisions don't just create new stars, they also reshape the galaxies involved. The gravitational forces at play can stretch and distort the galaxies, creating long tidal tails of stars and gas that extend far beyond their original boundaries. These tails are often the most visible signs of a collision, painting a vivid picture of the immense forces at work. Over time, the galaxies settle into a new equilibrium, often forming an elliptical galaxy, which is smoother and more featureless than the spiral galaxies that may have collided. Interestingly, these collisions also have a profound impact on the supermassive black holes at the centers of galaxies. As the galaxies merge, their central black holes are drawn together, eventually spiraling inward and merging themselves. This process releases gravitational waves, ripples in spacetime that can be detected by observatories here on Earth. The merger of supermassive black holes is one of the most energetic events in the universe, and it plays a key role in shaping the final structure of the newly formed galaxy. Galactic collisions remind us that the universe is a dynamic, ever-changing place. They are not just destructive events but also creative ones, driving the evolution of galaxies and giving rise to new stars, new structures, and even new galaxies. As we look to the future collision of the Milky Way and Andromeda, we catch a glimpse of the cosmic processes that have shaped the universe for billions of years and will continue to do so for billions more. Now, let's turn our attention to one of the most fundamental processes in the universe: star formation. Galaxies are not just collections of stars, they are the cosmic nurseries where stars are born. Within these vast structures, the conditions for star formation are created, setting the stage for the birth of new suns that will light up the cosmos. At the heart of star formation are dense molecular clouds, often referred to as stellar nurseries. These clouds are made up of gas, primarily hydrogen, and dust, and they can span hundreds of light years across. Despite their immense size, these clouds are incredibly cold, with temperatures dropping to just a few degrees above absolute zero. It's within these frigid, dark regions that the magic of star formation begins. The process starts when something disturbs the cloud, such as a nearby supernova explosion or the gravitational pull of a passing galaxy. This disturbance causes the gas and dust within the cloud to clump together. As these clumps grow denser, their gravitational pull becomes stronger, drawing in more material. Over time, the clumps collapse under their own gravity, forming what's known as a protostar, a baby star in the making. As the protostar continues to gather mass, its core heats up due to the increasing pressure. Once the temperature in the core reaches about 10 million degrees Celsius, nuclear fusion ignites. This is the moment a star is truly born, as hydrogen atoms fuse together to form helium, releasing vast amounts of energy in the form of light and heat. The newborn star begins to shine, illuminating the surrounding gas and dust and carving out a space for itself within the galaxy. But star formation doesn't happen in isolation. Often, these stellar nurseries give birth to not just one star, but entire clusters of stars. These clusters can range from a few dozen stars to tens of thousands, all born from the same molecular cloud. Over time, these stars may drift apart, but their shared origin leaves a lasting imprint on their composition and motion. Interestingly, the rate of star formation in a galaxy can vary dramatically. Some galaxies, known as starburst galaxies, are undergoing an intense period of star formation, producing stars at a rate hundreds or even thousands of times faster than our own Milky Way. These galaxies are often the result of collisions or interactions with other galaxies, which compress gas and trigger a frenzy of star birth. On the other hand, some galaxies, particularly older elliptical ones, have very little star formation occurring, as most of their gas has already been used up or blown away. Star formation is a delicate balance of forces: gravity pulling material together, while pressure and radiation push it apart. It's a process that shapes not only the stars themselves, but also the galaxies they inhabit. Without star formation, galaxies would be dark, lifeless places. But thanks to these cosmic nurseries, the universe is filled with the light of countless stars, each one a testament to the incredible processes that take place within galaxies. As we continue our journey through the mysteries of galaxy formation and evolution, let's explore how these stars, once formed, play a role in shaping the very galaxies they call home. Now, let's take a closer look at one of the most fascinating processes in the life cycle of a galaxy: galactic recycling. Just as nature recycles resources on Earth, galaxies have their own way of reusing materials to create new stars, planets, and even life itself. This process is driven by two powerful forces: supernova and stellar winds. When a massive star reaches the end of its life, it doesn't fade away quietly. Instead, it goes out with a spectacular explosion known as a supernova. These explosions are so powerful that they can outshine entire galaxies for a brief moment. But the real magic happens in the aftermath. A supernova scatters the star's outer layers into space, releasing a mix of heavy elements like carbon, oxygen, iron, and even gold. These elements, forged in the heart of the star during its lifetime, are now flung into the surrounding interstellar medium, the vast space between stars filled with gas and dust. Stellar winds, on the other hand, are streams of charged particles that flow from the surfaces of stars, especially massive ones. These winds carry away lighter elements like hydrogen and helium, as well as some heavier elements, and deposit them into the interstellar medium. Over time, this material mixes with the gas and dust already present, creating a richer, more complex environment. This enriched interstellar medium becomes the raw material for the next generation of stars and planets. When new stars form, they incorporate these heavy elements into their composition. Planets, including rocky ones like Earth, are born from the same material. In fact, the iron in your blood, the calcium in your bones, and the silicon in the ground beneath your feet all originated in the hearts of ancient stars that exploded long ago. Without galactic recycling, these elements would remain locked away, and the universe as we know it would look very different, but the process doesn't stop there. As new stars form and evolve, they continue to contribute to the cycle. Some stars, like our Sun, will eventually shed their outer layers in a more gentle process, adding even more material to the interstellar medium. Others will end their lives in supernova, continuing the cycle of enrichment. This ongoing exchange of material ensures that galaxies remain dynamic, ever-changing environments where new stars and planets can form. Galactic recycling is a testament to the interconnectedness of the universe. It shows how the life and death of stars are not isolated events but part of a grand cosmic cycle that shapes the evolution of galaxies. As we move forward, let's explore how these recycled materials play a role in the larger structure of the universe, weaving together the story of galaxy formation and evolution in ways that continue to amaze and inspire. Now, let's shift our focus to an often overlooked yet crucial player in the cosmic drama: magnetic fields. While they might seem invisible and intangible, magnetic fields are powerful forces that shape the very fabric of galaxies. These fields stretch across vast distances, weaving through the interstellar medium and influencing how gas moves, how stars form, and even how galaxies take on their iconic shapes. Magnetic fields are born from the motion of charged particles like electrons and protons within galaxies. As these particles move, they generate electric currents, which in turn create magnetic fields. Over time, these fields grow stronger and more complex, intertwining with the gas and dust that fill the space between stars. But what makes them so important? Well, magnetic fields act like cosmic traffic controllers, guiding the flow of gas and dust in ways that can either promote or hinder star formation. For example, in spiral galaxies, magnetic fields play a key role in shaping those beautiful, swirling arms we often see in images. These fields help channel gas into dense regions where gravity can take over and collapse the material into new stars. Without magnetic fields, the gas might spread out too thinly, making it harder for stars to form. In this way, magnetic fields are like invisible sculptors, helping to carve out the intricate structures we associate with spiral galaxies. But their influence doesn't stop there. Magnetic fields also help regulate the movement of gas within galaxies, preventing it from collapsing too quickly or dispersing too widely. This delicate balance is essential for maintaining the steady pace of star formation we observe in many galaxies. In some cases, magnetic fields can even protect gas clouds from being torn apart by the intense radiation or winds from nearby stars, ensuring that these clouds remain intact long enough to form new stars and planets. Interestingly, magnetic fields also play a role in the larger-scale evolution of galaxies. When galaxies collide or interact, their magnetic fields can become tangled and amplified, triggering bursts of star formation or even feeding the supermassive black holes at their centers. These interactions can leave lasting imprints on the galaxies, shaping their structure and influencing their future evolution. So, while magnetic fields might not be as flashy as supernova or as mysterious as dark matter, they are fundamental to the story of galaxy formation and evolution. They remind us that even the unseen forces of the universe have a profound impact on the cosmic landscape. As we continue our journey, let's explore how these magnetic fields interact with other cosmic phenomena to create the galaxies we see today and those that will form in the distant future. Now, let's turn our attention to a phenomenon that can dramatically alter the fate of galaxies' galactic winds and outflows. These powerful forces, driven by the explosive energy of supernova and the intense activity of supermassive black holes, have the ability to reshape entire galaxies. Imagine a cosmic storm sweeping through the galaxy and carrying away vast amounts of gas, the very material needed to form new stars. This is the reality of galactic winds, and their impact is nothing short of extraordinary. When a massive star reaches the end of its life and explodes as a supernova, it releases an enormous amount of energy. This energy doesn't just fade away, it creates shock waves that push gas outward at incredible speeds. These winds can travel thousands of light years, carrying gas and dust far beyond the galaxy's boundaries. In some cases, this gas is lost forever, leaving the galaxy with fewer resources to form new stars. Over time, this can slow down or even halt star formation altogether, effectively putting the galaxy into a kind of cosmic retirement. But supernova aren't the only drivers of these winds. At the heart of many galaxies lies a supermassive black hole, surrounded by a swirling disk of gas and dust. When this material falls into the black hole, it doesn't go quietly. It releases tremendous amounts of energy, creating what's known as an active galactic nucleus. This energy can generate winds so powerful that they push gas out of the galaxy at speeds approaching millions of miles per hour. These outflows can strip away entire clouds of gas, depriving the galaxy of the raw materials needed for future star formation. Interestingly, these winds and outflows don't just remove gas, they can also trigger new star formation in unexpected ways. As the winds sweep through the galaxy, they compress gas in certain regions, creating dense pockets where gravity can take over and form new stars. In this way, galactic winds can act as both destroyers and creators, shaping the galaxy in complex and often unpredictable ways. The effects of these winds extend far beyond individual galaxies. As gas is blown out into intergalactic space, it enriches the surrounding environment with heavy elements forged in the hearts of stars. This material can eventually become part of new galaxies, seeding them with the ingredients needed for planets and perhaps even life. In this way, galactic winds play a crucial role in the cosmic cycle of matter, connecting galaxies across vast distances and timescales. So, while galactic winds and outflows might seem like destructive forces, they are also essential players in the ongoing story of galaxy evolution. They remind us that even the most violent events in the universe can have far-reaching and often surprising consequences. As we continue to explore the mysteries of galaxy formation, these winds serve as a powerful reminder of the dynamic and ever-changing nature of the cosmos. Now, shifting our gaze to the broader picture, let's explore the Hubble sequence, a remarkable tool that has revolutionized how we classify and understand galaxies. Developed by the legendary astronomer Edwin Hubble in the early 20th century, this system organizes galaxies into distinct categories based on their shapes, offering a framework that helps us unravel the mysteries of their formation and evolution. At its core, the Hubble sequence divides galaxies into three main types: spiral, elliptical, and irregular. Spiral galaxies, like our own Milky Way, are characterized by their iconic swirling arms, which are often filled with young, bright stars and vast clouds of gas and dust. These arms are not static, they are dynamic regions where new stars are born, making spiral galaxies some of the most active and vibrant in the universe. On the other end of the spectrum are elliptical galaxies, which appear smooth and featureless, resembling glowing footballs of stars. These galaxies are typically older, with little gas or dust left to form new stars, giving them a more subdued appearance. Finally, there are irregular galaxies, which defy the neat categories of spirals and ellipticals. These galaxies often have chaotic shapes, the result of gravitational interactions or collisions with other galaxies. But the Hubble sequence is more than just a way to categorize galaxies by their appearance. It also provides clues about their life stories. For example, spiral galaxies are often rich in gas and dust, making them hotbeds of star formation. Over time, as they exhaust their gas reserves or undergo collisions, they may evolve into elliptical galaxies, which are dominated by older stars and have little ongoing star formation. Irregular galaxies, on the other hand, often represent galaxies in transition, caught in the midst of dramatic changes caused by gravitational encounters or mergers. This classification system has become an indispensable tool for astronomers, helping them trace the evolutionary paths of galaxies across billions of years. By studying where a galaxy falls on the Hubble sequence, scientists can infer its history from its formation to its interactions with other galaxies. It's like reading a cosmic biography where each shape tells a story of birth, growth, and transformation. The Hubble sequence also highlights the incredible diversity of galaxies in the universe. From the elegant spirals to the stately ellipticals and the chaotic irregulars, each type offers a unique window into the processes that shape galaxies. And as our telescopes grow more powerful, allowing us to peer deeper into space and further back in time, the Hubble sequence continues to guide our understanding of how galaxies evolve, adapt, and interact in the vast cosmic dance. So, the next time you gaze at an image of a galaxy, remember that its shape is more than just a snapshot. It's a chapter in the ongoing story of the universe, a story that the Hubble sequence helps us decode one galaxy at a time. Now, let's zoom in on one of the unsung heroes of the cosmic story, dwarf galaxies. These small, often overlooked galaxies play a crucial role in the grand tapestry of the universe. While they may not have the grandeur of spirals or the sheer size of ellipticals, dwarf galaxies are the building blocks of the cosmos, quietly shaping the universe as we know it. Dwarf galaxies are much smaller than their larger counterparts, often containing only a few billion stars compared to the hundreds of billions found in galaxies like the Milky Way. But don't let their size fool you. These tiny galaxies are incredibly important. In fact, they are thought to be some of the earliest structures to form in the universe, emerging just a few 100 million years after the Big Bang. Their small size and relatively simple structure make them ideal laboratories for studying the early universe and the processes that led to the formation of larger galaxies. One of the most fascinating aspects of dwarf galaxies is their role in galactic mergers. Over billions of years, these small galaxies collide and merge with larger ones, contributing their stars, gas, and dark matter to the growing structure. This process, known as hierarchical galaxy formation, is how many of the massive galaxies we see today came to be. For example, the Milky Way itself is thought to have grown by consuming dozens of dwarf galaxies over its lifetime, with some, like the Sagittarius dwarf galaxy, still in the process of being absorbed. But dwarf galaxies aren't just fuel for larger galaxies. They also play a key role in shaping the universe's large-scale structure. They are often found orbiting larger galaxies, forming what astronomers call satellite systems. These satellite galaxies can influence the evolution of their host galaxies through gravitational interactions, triggering star formation or even stripping away gas and dust. In some cases, they can also help astronomers map the distribution of dark matter, as their movements are influenced by the invisible gravitational pull of this mysterious substance. Despite their importance, dwarf galaxies remain some of the most challenging objects to study. Their faint light and small size make them difficult to observe, especially at great distances. However, advancements in telescope technology, like the James Webb Space Telescope, are beginning to shed light on these elusive objects, revealing new details about their formation, evolution, and role in the cosmic hierarchy. So, while dwarf galaxies may not steal the spotlight like their larger cousins, they are essential players in the story of the universe, from their role as cosmic building blocks to their influence on the growth and evolution of larger galaxies. These tiny structures remind us that even the smallest things can have a profound impact on the grandest scales. And as we continue to explore the cosmos, dwarf galaxies will undoubtedly reveal even more secrets about the origins and evolution of the universe. Now, let's step back and take a look at the universe on its grandest scale, the cosmic web. Imagine the universe not as a random scattering of galaxies, but as an intricate, interconnected network, much like a spider's web stretched across the cosmos. This vast structure, known as the cosmic web, is the backbone of the universe, shaping where galaxies form and how they evolve. The cosmic web is made up of long, thread-like filaments of dark matter and gas stretching across billions of light years. These filaments intersect at dense nodes, creating a web-like pattern that spans the entire universe. Galaxies, including our own Milky Way, form along these filaments like beads strung on a cosmic necklace. The densest regions where filaments meet become the homes of galaxy clusters and superclusters, while the emptier spaces between the filaments are vast cosmic voids nearly devoid of matter. But how does this cosmic web form? It all goes back to the early universe, just moments after the Big Bang. Tiny fluctuations in the density of matter, amplified by gravity, began to pull matter together into clumps. Over billions of years, these clumps grew into the filaments and nodes we see today. Dark matter, with its invisible gravitational pull, played a crucial role in shaping this structure, acting as the scaffolding upon which ordinary matter could gather and form galaxies. One of the most fascinating aspects of the cosmic web is how it influences the formation and evolution of galaxies. Galaxies that form along filaments are often funneled toward the nodes, where they can collide and merge, creating even larger galaxies. This process is a key part of how the universe's large-scale structure evolves over time. Even the Milky Way is thought to reside within a filament of the cosmic web, slowly being drawn toward the Virgo cluster, one of the largest structures in our cosmic neighborhood. Studying the cosmic web is no easy task, as it spans such vast distances and is largely invisible to traditional telescopes. However, astronomers use techniques like mapping the distribution of galaxies and observing the faint glow of hydrogen gas to trace the outlines of this immense network. Recent advancements, such as the use of supercomputers to simulate the universe's evolution, have given us unprecedented insights into the cosmic web structure and its role in shaping the cosmos. The cosmic web reminds us that the universe is not just a collection of isolated galaxies, but a dynamic, interconnected system. It's a testament to the power of gravity and the intricate processes that have shaped the universe over billions of years. And as we continue to explore this vast network, we uncover more about the forces that govern the cosmos and our place within it. Now, let's zoom in a bit closer to explore how galaxies don't just exist in isolation. They come together in massive gatherings known as galaxy clusters and superclusters. Picture a bustling city where individual buildings are like galaxies, and the city itself is a galaxy cluster. These clusters are some of the largest structures in the universe, bound together by the relentless pull of gravity. Galaxy clusters can contain anywhere from a few dozen to thousands of galaxies, all swirling around a common center, but it doesn't stop there. These clusters themselves group together into even larger structures called superclusters, which can span hundreds of millions of light years. For example, our own Milky Way is part of a supercluster known as Laniakea, which contains around 100,000 galaxies. It's like a cosmic metropolis on an unimaginable scale. So, how do these clusters and superclusters influence galaxy evolution? The answer lies in their gravitational interactions. Within a cluster, galaxies are constantly tugging at each other, sometimes colliding and merging. These collisions can trigger bursts of star formation, reshape galaxies, and even create entirely new structures. Over time, these interactions can transform spiral galaxies into elliptical ones or strip away gas and dust, halting star formation altogether. But the influence of clusters and superclusters goes beyond just individual galaxies. The immense gravity of these structures can also affect the surrounding cosmic environment. For instance, the hot gas trapped within clusters emits powerful X-rays, and the gravitational pull of these massive structures can bend light, creating phenomena like gravitational lensing. This allows us to see distant galaxies that would otherwise be hidden from view. Interestingly, galaxy clusters and superclusters also act as cosmic signposts, helping astronomers map the large-scale structure of the universe. By studying their distribution, we can trace the outlines of the cosmic web and better understand how the universe has evolved over billions of years. It's a reminder that galaxies are not just isolated islands in space, they are part of a vast, interconnected network, shaped by the forces of gravity and the relentless dance of cosmic evolution. As we continue to study these colossal structures, we uncover more about the processes that drive galaxy formation and the intricate relationships that bind the universe together. From the smallest dwarf galaxies to the largest superclusters, every piece of this cosmic puzzle helps us understand the grand story of the cosmos. Now, let's turn our gaze to the distant future and ponder the ultimate fate of galaxies. Over trillions of years, the universe will undergo dramatic changes, and galaxies will not remain as we see them today. One of the most significant shifts will be the gradual fading of star formation. As galaxies consume their gas and dust, the raw materials needed to create new stars, the process of star birth will slow down and eventually come to a halt. Imagine a galaxy that once sparkled with the light of countless stars, now growing dimmer as its stellar nurseries fall silent. In this far-off era, elliptical galaxies will dominate the cosmic landscape. These massive, smooth galaxies, which form through the collisions and mergers of smaller galaxies, will become the primary inhabitants of the universe. Unlike spiral galaxies, which rely on gas-rich environments to fuel star formation, elliptical galaxies are largely devoid of such material. Their stars will age and cool, turning into faint red dwarfs or even black holes, leaving these galaxies as quiet, dark relics of a once vibrant universe. But the story doesn't end there. Over even longer timescales, galaxies themselves may begin to dissolve. As the universe continues to expand, driven by the mysterious force of dark energy, the gravitational bonds that hold galaxies together will weaken. Stars may drift apart, and galaxies could lose their cohesive structure, scattering their remnants across the void. It's a sobering thought, a universe where the majestic galaxies we know today are reduced to isolated stars and dark, cold remnants. Yet, even in this distant future, the legacy of galaxies will endure. The heavy elements forged in their stars, carbon, oxygen, iron, and more, will remain scattered across the cosmos. These elements are the building blocks of planets, life, and even future generations of stars, ensuring that the story of galaxies continues to shape the universe in ways we can only begin to imagine. As we reflect on the fate of galaxies, we're reminded of the impermanence of even the grandest cosmic structures. But it's also a testament to the incredible processes that have shaped the universe over billions of years, and the enduring impact of galaxies on the fabric of space and time. Next, we'll take a closer look at our own galactic home, the Milky Way, and explore its unique journey through the cosmos. Now, let's zoom in closer to home and explore the fascinating story of our own galaxy, the Milky Way. This vast spiral of stars, gas, and dust has a history that stretches back more than 13 billion years, and its evolution is a tale of cosmic collisions, star formation, and galactic transformation. The Milky Way began its life as a collection of smaller protogalaxies, clumps of gas and dark matter that merged together under the pull of gravity. Over time, these early building blocks coalesced into the spiral galaxy we recognize today. But the Milky Way didn't grow in isolation. Throughout its history, it has absorbed smaller galaxies, a process known as galactic cannibalism. One of the most notable examples is the Gaia Enceladus galaxy, which collided with the Milky Way around 10 billion years ago. This ancient merger not only added stars to our galaxy, but also played a key role in shaping its structure and triggering bursts of star formation. As the Milky Way continued to evolve, it developed its iconic spiral arms, regions of dense gas and dust where new stars are born. These arms are not static, they ripple outward like waves, driven by the gravitational interactions of stars and dark matter. At the heart of the galaxy lies a supermassive black hole, Sagittarius, a star, which influences the motion of stars and gas in its vicinity. But the Milky Way story is far from over. In about 4.5 billion years, it will collide with its nearest galactic neighbor, the Andromeda Galaxy. This cosmic event will be one of the most dramatic in the history of our galaxy. As the two spiral galaxies merge, their stars will be flung into new orbits and their gas clouds will collide, igniting a burst of new star formation. Over time, the Milky Way and Andromeda will combine to form a single, massive elliptical galaxy, often referred to as Milkomeda. This future merger is a reminder that galaxies are not static entities but dynamic systems, constantly evolving through interactions and collisions. The Milky Way's journey, from its humble beginnings as a collection of proto-galaxies to its eventual merger with Andromeda, highlights the ever-changing nature of the cosmos. As we reflect on the Milky Way's past and future, we gain a deeper appreciation for the forces that shape galaxies and the intricate dance of gravity, dark matter, and star formation that defines their evolution. Next, we'll take a closer look at Andromeda, our galactic neighbor, and uncover the secrets of its own cosmic journey. Now, let's turn our gaze toward the Andromeda Galaxy, our closest galactic neighbor and a key player in the cosmic story. Located approximately 2.5 million light-years away, Andromeda is not only the largest galaxy in our local group, but also a fascinating mirror to our own Milky Way. Like the Milky Way, Andromeda is a spiral galaxy with sweeping arms of stars, gas, and dust spiraling outward from its bright core. But while they share this basic structure, the two galaxies have followed distinct evolutionary paths that make Andromeda a unique cosmic treasure. Andromeda's origins trace back to the early universe, just like the Milky Way. It formed from the merging of smaller proto-galaxies, growing over billions of years through a series of collisions and mergers. However, Andromeda's history has been even more tumultuous than our own galaxies. Astronomers believe that Andromeda has absorbed dozens of smaller galaxies over its lifetime, making it significantly larger and more massive than the Milky Way. This galactic cannibalism has left behind a trail of evidence, including streams of stars and ancient globular clusters that hint at its violent past. One of the most striking differences between Andromeda and the Milky Way lies in their central regions. While both galaxies host supermassive black holes, Andromeda's black hole is far more active, emitting powerful jets of energy that influence its surroundings. This activity has shaped Andromeda's core into a bustling hub of star formation and stellar activity, contrasting with the relatively quieter center of the Milky Way. Another key difference is Andromeda's size and brightness. With over 1 trillion stars, Andromeda is nearly twice as large as the Milky Way and shines more brightly in the night sky. Its immense size and luminosity make it a favorite target for amateur astronomers, who can spot it with the naked eye under dark skies. Despite these differences, Andromeda and the Milky Way share a common destiny. As we've already touched on, the two galaxies are on a collision course, set to merge in about 4.5 billion years. This future event will not only reshape both galaxies, but also create a new, larger elliptical galaxy, Milkomeda. The similarities and differences between Andromeda and the Milky Way make their impending collision all the more intriguing, as it will be a cosmic dance between two giants, each with its own unique history and character. As we explore Andromeda's formation and evolution, we gain a deeper understanding of the forces that shape galaxies and the interconnected nature of the universe. Next, we'll dive into the role of quasars, the brilliant beacons powered by supermassive black holes, and how they influence the evolution of galaxies like Andromeda and the Milky Way. Now, shifting our focus to one of the most energetic phenomena in the universe, let's explore the role of quasars in shaping galaxies. Quasars, short for quasi-stellar radio sources, are among the brightest objects in the cosmos, powered by supermassive black holes at the centers of galaxies. These black holes, millions or even billions of times more massive than our Sun, devour surrounding gas and dust, releasing staggering amounts of energy in the process. This energy doesn't just vanish into the void, it plays a crucial role in the evolution of galaxies. As quasars emit intense radiation and powerful jets of particles, they can heat up the surrounding gas in their host galaxies. This heating process has a profound effect on star formation. In some cases, the energy from quasars can prevent gas from cooling and collapsing into new stars, effectively putting a pause on star formation. This might sound counterintuitive, but it's a key way quasars regulate the growth of their galaxies. Without this regulation, galaxies could exhaust their gas supply too quickly, leading to a burst of star formation followed by a long, quiet period. On the other hand, quasars can also trigger star formation in certain regions. The shock waves from their jets can compress gas clouds, creating the perfect conditions for new stars to ignite. This dual role, both suppressing and encouraging star formation, makes quasars a fascinating force in galaxy evolution. They act as cosmic regulators, balancing the growth and activity of their host galaxies over billions of years. Quasars also provide a window into the early universe. Because they are so bright, we can observe them at incredible distances, giving us a glimpse of galaxies in their infancy. By studying quasars, astronomers can piece together how galaxies formed and evolved over time, shedding light on the processes that shaped the universe as we know it today. As we continue to unravel the mysteries of quasars, we gain a deeper appreciation for their role in the cosmic dance of galaxy formation and evolution. Next, we'll delve into the fascinating field of galactic archaeology, where ancient stars hold the secrets to the history of galaxies. Now, let's step into the fascinating world of galactic archaeology, a field where astronomers act as cosmic detectives, uncovering the secrets of galaxy formation by studying ancient stars. Just as archaeologists dig through layers of Earth's history to understand our past, galactic archaeologists examine the oldest stars in the universe to piece together the story of how galaxies came to be. These ancient stars, often referred to as stellar fossils, hold clues about the conditions and processes that shaped galaxies billions of years ago. One of the key tools in galactic archaeology is the study of stellar populations. Stars within a galaxy can be grouped into different generations based on their age and chemical composition. The oldest stars, known as population 2 stars, are metal-poor, meaning they contain fewer heavy elements like iron and carbon. These stars formed early in the universe's history, when the cosmos was still young and pristine. By analyzing their light, astronomers can determine their age, composition, and even their motion, providing insights into the environment in which they formed. Population 1 stars, on the other hand, are younger and richer in heavy elements. These stars formed later, after earlier generations of stars had lived, died, and enriched the interstellar medium with the elements forged in their cores. By comparing these stellar populations, galactic archaeologists can trace the timeline of galaxy formation, revealing how galaxies grew and evolved over billions of years. Another powerful technique in galactic archaeology is the study of globular clusters, dense groups of ancient stars that orbit galaxies like the Milky Way. These clusters are like time capsules preserving the conditions of the early universe. By examining their stars, astronomers can reconstruct the history of galaxy mergers, star formation bursts, and even the distribution of dark matter. Galactic archaeology also relies on advanced telescopes and instruments such as the Gaia mission, which maps the positions, distances, and motions of over 1 billion stars in our galaxy. This data allows astronomers to trace the orbits of ancient stars, revealing how they were influenced by past galactic collisions and interactions. It's like rewinding the cosmic clock to see how galaxies assembled themselves over time. Through galactic archaeology, we gain a deeper understanding of the universe's history, from the formation of the first stars to the complex structures we see today. It's a field that connects the distant past with the present, offering a unique perspective on the evolution of galaxies. Next, we'll explore the mysterious world of ultra-diffuse galaxies, where size and brightness don't always go hand in hand. Now, let's turn our attention to one of the most puzzling mysteries in the cosmos, ultra-diffuse galaxies. These galaxies are enormous in size, often as large as the Milky Way, but they're incredibly faint, emitting only a fraction of the light we'd expect from such massive structures. Imagine a galaxy so spread out that its stars are scattered like fireflies in the night sky, barely visible against the vast darkness of space. That's the essence of an ultra-diffuse galaxy. So, how do these ghostly galaxies form? One leading theory suggests they might be the remnants of larger galaxies that were stripped of their gas and stars through gravitational interactions with neighboring galaxies. Over time, these interactions could have stretched the galaxy thin, leaving behind a faint, diffuse structure. Another possibility is that ultra-diffuse galaxies formed in regions of the universe where dark matter is sparse. Without the gravitational pull of dark matter to hold them together, these galaxies may have never condensed into the bright, tightly packed structures we're more familiar with. Interestingly, ultra-diffuse galaxies challenge our understanding of galaxy formation because they don't fit neatly into the categories we've established. They're not quite spirals, nor are they ellipticals, and their faintness makes them difficult to study. Yet, despite their elusive nature, astronomers have managed to uncover some fascinating details. For example, some ultra-diffuse galaxies appear to have an unusually high number of globular clusters, those dense groups of ancient stars we discussed earlier. This suggests that, despite their faintness, these galaxies might have a rich and complex history. The study of ultra-diffuse galaxies also raises questions about the role of dark matter. While most galaxies are thought to be embedded in massive halos of dark matter, some ultra-diffuse galaxies seem to have very little of it, if any at all. This has led scientists to wonder whether these galaxies could be a window into a different kind of cosmic evolution, one where dark matter plays a less dominant role. As we continue to explore these enigmatic structures, they remind us that the universe is full of surprises. Ultra-diffuse galaxies challenge our assumptions and push us to rethink what we know about how galaxies form and evolve. Next, we'll delve into the impact of dark energy, a mysterious force that's shaping the fate of galaxies across the universe. Now, shifting our focus to one of the most profound forces shaping the cosmos, let's explore the impact of dark energy. This mysterious force is responsible for the accelerated expansion of the universe, and its influence extends far beyond just pushing galaxies apart. It's reshaping the very fabric of the cosmos. Picture the universe as a stretching canvas with dark energy acting like an invisible hand, pulling it apart faster and faster over time. But what does this mean for galaxies? As dark energy drives the universe to expand at an increasing rate, it creates a kind of cosmic tug of war. On one side, gravity tries to pull galaxies together, forming clusters and superclusters. On the other, dark energy works to push them apart, stretching the space between them. Over time, this battle has profound consequences. For instance, as the universe expands, galaxies that are not bound by gravity to a cluster will drift farther and farther apart, eventually becoming isolated islands in the vastness of space. This expansion also affects the future of galaxy formation. In the early universe, gravity dominated, allowing galaxies to form and grow through mergers and collisions. But as dark energy takes over, these processes slow down. The space between galaxies grows so vast that future collisions become increasingly rare. This means that the era of galaxy mergers, which has shaped much of the universe's history, is gradually coming to an end. In the distant future, galaxies may evolve in isolation, with fewer opportunities to grow or change through interactions. Dark energy also influences the large-scale structure of the universe. The cosmic web, the intricate network of filaments and voids that galaxies are arranged along, is shaped by the interplay between gravity and dark energy. As dark energy accelerates the expansion, it stretches these filaments, making the voids between them larger and more pronounced. Over billions of years, this could lead to a universe where galaxies are spread out in a more diffuse and sparse pattern. But perhaps the most intriguing aspect of dark energy is how little we truly understand it. We know it exists because of its effects on the universe's expansion, but its nature remains one of the greatest mysteries in science. Is it a property of space itself, or is it something entirely different? Answering these questions could revolutionize our understanding of the cosmos and the fate of galaxies within it. As we ponder the role of dark energy, it's clear that this force is not just shaping the universe today, it's determining its ultimate destiny. Next, we'll take a closer look at galactic cannibalism in action, examining how larger galaxies consume smaller ones to grow and evolve. Now, let's zoom in on a cosmic phenomenon that's as dramatic as it sounds: galactic cannibalism in action. One of the most striking examples of this process is happening right in our own galactic neighborhood. The Milky Way, our home galaxy, is currently in the process of absorbing the Canis major dwarf galaxy, a smaller galaxy that's being slowly torn apart by the Milky Way's immense gravitational pull. The Canis major dwarf galaxy is what astronomers call a satellite galaxy, meaning it orbits the Milky Way. Over time, the gravitational forces from our galaxy have stretched and distorted it, pulling stars and gas away from its core. This process isn't sudden or violent. It's a slow, relentless tug of war that has been unfolding for hundreds of millions of years. As the Milky Way's gravity pulls in material from the Canis major dwarf, it leaves behind a trail of stars and debris, creating a faint stream of light that astronomers can observe. This isn't just a one-time event, it's part of a larger pattern. The Milky Way has a history of consuming smaller galaxies, and each merger leaves its mark. For example, the remnants of past galactic meals can still be seen in the form of star streams and clusters scattered throughout our galaxy. These cosmic leftovers are like fossils, telling the story of the Milky Way's growth over billions of years. But why does this happen? Galactic cannibalism is driven by gravity. Larger galaxies like the Milky Way have stronger gravitational fields which allow them to pull in smaller neighbors. Over time, these smaller galaxies are stripped of their stars and gas, which are then incorporated into the larger galaxy. This process not only helps the Milky Way grow, but also enriches it with new material, fueling the formation of new stars and planets. Interestingly, this isn't just a one-way street. While the Milky Way is consuming the Canis major dwarf galaxy, it's also being influenced by it. The gravitational interaction between the two galaxies can trigger bursts of star formation and even alter the structure of the Milky Way's spiral arms. It's a dynamic process that shapes both galaxies in profound ways. As we look to the future, the Canis major dwarf galaxy will continue to be absorbed, eventually becoming a part of the Milky Way's history. But this isn't the end of the story. Our galaxy is on a collision course with the Andromeda galaxy, an event that will redefine both galaxies in ways we can only begin to imagine. For now, though, the Milky Way's ongoing feast on the Canis major dwarf galaxy serves as a vivid reminder of the dynamic and ever-changing nature of the cosmos. Next, we'll explore how supernovae play a crucial role in shaping galaxies, dispersing heavy elements and triggering new star formation. Now, let's turn our attention to one of the most explosive events in the universe, supernova. These colossal stellar explosions don't just light up the cosmos, they play a pivotal role in shaping galaxies. When a massive star reaches the end of its life, it doesn't fade quietly. Instead, it goes out with a bang, releasing an incredible amount of energy and scattering its material across space. This material, rich in heavy elements like iron, gold, and uranium, is crucial for the formation of new stars, planets, and even life itself. Supernovae act as cosmic recyclers. The shock waves from these explosions travel through the surrounding gas and dust, compressing it and triggering the collapse of dense regions. This compression is the first step in the birth of new stars. Without supernova, galaxies would lack the raw materials needed to form the next generation of stars and planetary systems. In a way, every star you see in the night sky owes its existence to the remnants of these ancient explosions. But the influence of supernova doesn't stop there. The heavy elements they produce are essential for the formation of rocky planets like Earth. Elements like carbon, oxygen, and nitrogen, which are vital for life, are forged in the hearts of stars and spread throughout the galaxy by supernova. This means that the very building blocks of life are a direct result of these stellar explosions. Without them, the universe would be a much simpler and far less interesting place. Interestingly, supernova also help regulate the structure of galaxies. The energy released by these explosions can heat up the surrounding gas, preventing it from cooling and collapsing too quickly. This process helps maintain a balance between star formation and the availability of gas in a galaxy. In some cases, supernova can even blow gas out of a galaxy entirely, slowing down star formation and influencing the galaxy's evolution over billions of years. As we look out into the universe, we see the fingerprints of supernova everywhere, from the colorful nebulae where new stars are born to the rocky planets that orbit them. These explosive events have left an indelible mark on the cosmos. Next, we'll explore how some galaxies develop bars of stars and gas, and how these structures influence star formation and galactic evolution. Now, shifting our focus to another fascinating feature of galaxies, let's talk about galactic bars. These are elongated structures made up of stars and gas that stretch across the centers of some galaxies, giving them a distinctive, barred appearance. But how do these bars form, and what role do they play in the life of a galaxy? Galactic bars typically emerge due to the gravitational interactions within a galaxy. As stars and gas orbit the center, their collective motion can create instabilities, causing the material to clump together and form a bar-like structure. This process is often driven by the galaxy's own rotation, which can stretch and align the stars and gas into a bar shape over time. Interestingly, bars are more common in spiral galaxies, and they can persist for billions of years, shaping the galaxy's evolution in profound ways. Once a bar forms, it acts like a cosmic traffic controller, funneling gas and dust toward the galaxy's center. This influx of material can trigger intense bursts of star formation, especially in the central regions of the galaxy. In fact, many barred galaxies have bright, star-forming regions near their cores, fueled by the gas that the bar has directed inward. This process not only creates new stars but also contributes to the growth of the galaxy's central bulge, a dense region of stars that often surrounds the supermassive black hole at the heart of the galaxy. But the influence of galactic bars doesn't stop there. They can also affect the overall structure of the galaxy over time. As the bar rotates, it can transfer angular momentum to the outer regions of the galaxy, causing the spiral arms to become more tightly wound. In some cases, the bar may even dissolve over billions of years, leaving behind a more featureless elliptical galaxy. This dynamic interplay between bars and their host galaxies highlights just how interconnected the processes of star formation and galactic evolution truly are. Galactic bars are a perfect example of how small-scale structures can have large-scale impacts. By channeling gas, triggering star formation, and reshaping galaxies, these bars play a crucial role in the cosmic dance of creation and transformation. Next, we'll explore how tidal forces from nearby galaxies can distort shapes, trigger star formation, and even strip away material, further shaping the evolution of galaxies. Now, let's turn our attention to the powerful influence of tidal forces, a phenomenon that can dramatically reshape galaxies over time. Tidal forces arise when the gravitational pull of one galaxy tugs on another, creating a stretching effect that can distort their shapes and even trigger significant changes in their structure. These forces are most noticeable when galaxies pass close to one another, and their effects can be both destructive and creative. When two galaxies interact, the gravitational pull between them can stretch and twist their shapes, often creating long, flowing streams of stars and gas known as tidal tails. These tails are a visible reminder of the immense forces at play, and they can stretch for thousands of light years across the cosmos. But tidal forces don't just alter appearances, they can also spark new activity within galaxies. As gas and dust are pulled and compressed by these forces, they can collapse under their own gravity, igniting bursts of star formation. This process often leads to the creation of bright, young star clusters, adding a splash of new light to the interacting galaxies. However, tidal forces can also have a more destructive side. In some cases, the gravitational tug of war between galaxies can strip away material entirely, leaving one or both galaxies significantly altered. For example, smaller galaxies that pass too close to larger ones may lose some of their gas and stars, which are then absorbed by the larger galaxy. This process, known as tidal stripping, can leave the smaller galaxy diminished and less capable of forming new stars in the future. Over time, repeated interactions can even lead to the complete disruption of smaller galaxies, their material scattered across the cosmos. Despite their destructive potential, tidal forces also play a vital role in the evolution of galaxies. By triggering star formation and redistributing material, they contribute to the dynamic and ever-changing nature of the universe. These interactions remind us that galaxies are not isolated islands in space but are deeply connected, constantly influencing and reshaping one another through the invisible threads of gravity. Next, we'll look ahead to the future of galaxy research and the exciting discoveries that await us with new telescopes and missions. Now, let's shift our gaze to the horizon of discovery, where the future of galaxy research promises to unlock even more secrets of the cosmos. One of the most exciting developments on this frontier is the James Webb Space Telescope, a groundbreaking observatory that's already transforming our understanding of galaxy formation and evolution. With its unprecedented ability to peer deep into the infrared spectrum, the James Webb Space Telescope allows us to see farther back in time than ever before, capturing light from the earliest galaxies that formed just after the Big Bang. This incredible tool is helping astronomers piece together the cosmic puzzle, revealing how galaxies grew and evolved over billions of years. But the James Webb Space Telescope is just the beginning. Upcoming missions like the Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission are set to expand our knowledge even further. The Nancy Grace Roman Space Telescope, for example, will map the universe in unprecedented detail, helping us understand the role of dark energy in shaping the large-scale structure of galaxies. Meanwhile, Euclid will focus on unraveling the mysteries of dark matter, the invisible force that holds galaxies together. Together, these missions will provide a more complete picture of how galaxies form, evolve, and interact within the cosmic web. On the ground, next-generation observatories like the extremely large telescope in Chile are also poised to make groundbreaking contributions. With its massive mirror, this telescope will capture incredibly detailed images of distant galaxies, allowing scientists to study their structures and star-forming regions in ways that were previously impossible. These advancements will not only deepen our understanding of galaxy formation, but also shed light on the processes that drive star birth, black hole growth, and the recycling of cosmic material. As we look to the future, it's clear that the next generation of telescopes and missions will revolutionize our understanding of the universe. They'll help us answer fundamental questions about how galaxies came to be, how they've changed over time, and what their ultimate fate might be. With each new discovery, we're not just learning about galaxies, we're uncovering the story of our cosmic origins. And as we continue to explore, one thing is certain: the universe still holds countless mysteries waiting to be revealed. Next, we'll venture into the realm of speculation, exploring how galaxy formation might differ in other universes if the multiverse theory holds true. Now, let's take a step beyond our universe and into the realm of the multiverse, a concept that stretches the boundaries of our imagination. If the multiverse theory holds true, it suggests that our universe is just one of countless others, each with its own unique set of physical laws and conditions. This raises a fascinating question: how might galaxy formation differ in these alternate universes? In some universes, the fundamental constants like the strength of gravity or the speed of light could be entirely different. Imagine a universe where gravity is much weaker. In such a place, matter might not clump together as easily, leading to fewer or smaller galaxies. On the other hand, a universe with stronger gravity could result in galaxies forming much earlier and growing to enormous sizes, creating structures far beyond anything we've observed in our own cosmos. Then there's the possibility of universes with different amounts of dark matter or dark energy. In a universe dominated by dark energy, galaxies might struggle to form at all, as the rapid expansion of space could pull matter apart before it has a chance to coalesce. Conversely, a universe rich in dark matter might see galaxies forming in dense, intricate networks, with stars and planets emerging in ways we can barely imagine. Even the very nature of time and space could vary. In some universes, time might flow differently, altering the pace of galaxy formation and evolution. Or space itself could have extra dimensions, leading to galaxies with shapes and structures that defy our current understanding. While these ideas might sound like science fiction, they challenge us to think creatively about the cosmos. If the multiverse exists, it could mean that galaxy formation isn't a one-size-fits-all process. Instead, it might be a diverse and dynamic phenomenon, shaped by the unique rules of each universe. This not only expands our understanding of galaxies, but also invites us to consider the infinite possibilities that lie beyond our own cosmic horizon. As we wrap up our journey through these 30 fascinating facts, one thing is clear: the story of galaxy formation and evolution is far from complete. With every discovery, we uncover new layers of complexity and wonder, reminding us that the universe is a place of endless mystery and beauty. So, what do you think lies beyond our universe? Could there be other galaxies, other worlds, or even other versions of ourselves? The answers may be out there, waiting to be discovered. If you enjoyed this cosmic adventure, don't forget to like, subscribe, and hit the notification bell for more space mysteries. Until next time, keep looking up. The universe has so much more to show us. As we bring this cosmic journey to a close, let's take a moment to reflect on the incredible story of galaxy formation and evolution. From the explosive birth of galaxies in the aftermath of the Big Bang to the intricate dance of galactic collisions, we've explored how these vast structures grow, change, and shape the universe around them. We've seen how dark matter's invisible hand guides their formation, how supermassive black holes influence their evolution, and how galaxies recycle material to birth new stars and planets. Each fact we've uncovered reveals a piece of the puzzle, showing us just how complex and beautiful the cosmos truly is. But the story doesn't end here. With every discovery, new questions arise, and the universe continues to surprise us. From the mysterious role of dark energy to the possibility of alternate universes with entirely different galactic landscapes, there's still so much to learn and explore. The study of galaxies is a reminder that the universe is a place of endless wonder, where even the smallest details can hold profound significance. If you've enjoyed this journey through the mysteries of galaxy formation and evolution, don't stop here. The universe is vast and there's always more to discover. Be sure to like this video, subscribe to the channel, and hit the notification bell so you never miss out on future space mysteries. Together, let's keep exploring the cosmos and uncovering its secrets. Until next time, keep looking up. The stars have so much more to show us.